Roman Shvydkoy from the University of Illinois in Chicago. Roman, the floor is yours.
Yeah, thank you. Thanks to the organizers for a kind invitation. It's really an honor to be here. First time in Norway as well, so a lot of things to explore. So I'm going to talk about mathematical theory of collective behavior. It's a relatively new subject, especially in the context of the models that I'm going to consider. Okay, but as a motivational example, let me show this slide. So this is a paper from late 80s by Craig Reynolds, who, at that time the computing capabilities were good enough to implement graphic design in movie production, right? And one of the beautiful pictures that people wanted to see is the flight of birds, this fluid motion of flocks or school of fish. But it was not clear what are the basic principles between the interaction between these animals to implement in the computer algorithms. So he was the sort of designer of that algorithm, and he postulated basically what we call now a three-zone model, which consists of three regions of interaction. At the center is the bird, or we call it agent, right? Because it could be a bird or could be maybe other entity, like opinion, for instance, of a person. So there are three zones. The inner core here is the repulsion zone, so just to prevent collisions. Then the intermediate zone is the alignment, which is actually should be wider than I drawn here. And then the outer zone is the attraction to keep the flock together. Okay, so pretty natural picture. Unfortunately, mathematically, it's very hard to describe what's going to happen here. I mean, it's even hard to describe what do we expect from this picture, because there are no natural steady state of this model. But what's interesting is that when you look at this flock of birds, right, and zoom in, you can see that in the bulk they're more or less aligned, right? They're more or less going in the same direction, and they react maybe to some external influences to change directions. So the question is, what would be the effect of this alignment force, which is local in its range, right, to the flag? So generally, alignment models on a discrete level can be described by this very sort of general-looking system of ODEs. So xi's are the agents, vi's the velocities, and the velocities obey this system where the square bracket represents some kind of environmental averaging, okay, centered around the agent. And si represents a set of strengths functions, communication strengths. So this can be expressed in many different ways, and we're going to see one specific example, which is called Cucker-Smale theorem, Cucker-Smale system. So what we expect from this is what is called the emergence. So suppose that this environmental averaging range is finite. Do we expect a formation of some kind of global pattern from initially disordered flock, right? I mean, it's kind of natural to expect that it will transition through some intermediate local alignment stage before reaching the global consensus. So central to my talk will be the model introduced by Cucker and Smale in 2007, which is sort of one of the simplest problems to analyze, at least mathematically. It basically gives you this alignment protocol where communication between agents is governed by, is regulated by communication kernel phi, which is a positive radially decaying kernel. And if I want to represent this in kind of this form, which is going to be natural for me in many different places, you can sort of take out this sum of the influences and put it all in the strengths function, and then what remains is this particular average. Okay? So why is this model so famous? Is because it was the first model that produced unconditional global flocking result without any additional assumption at any time. So somehow before people looked at things like connectivity, and we're going to talk about it, of course, in order to reach global consensus. Now this model, provided the kernel has global reach, okay? So specifically, they looked at this particular power law, and if the tail of the kernel is non-integrable, then the flock is going to align, and the diameter of the flock in the open space will remain finite. This was extended and generalized to much more general kernels by Ha-Tadmor and Ha-Liu in the following years, and was also extended to other levels of description. Kinetic level by Carrier, Farnaziers, Rosado Toscani, and then macroscopic version, hydrodynamic version by Tan and Tadmor. So in other words, and this actually is sharp. So if beta is bigger than 1, then you can produce a flock which will not align. Okay, it's a criterion. So after the inception of this model, it has seen a lot of success. Don't really have time to go through these applications, but one notable example here is this paper by a group of engineers who implemented the Cucker and Smale model for the communication protocol between satellites in space, which are supposed to take pictures of remote planets. And they even computed the power beta to be 0.4. Okay, so that was the most fuel efficient communication strengths that allows you still to take synchronized pictures. There are a lot of applications to decentralized control, to swarm-based optimization. People use machine learning to read off specific shapes of the kernels to fit various data. So a lot of interesting applications. So the central to my talk is going to be the problem of emergence that I stated in the beginning. What about local communication? When can we say that local communication implies flocking? Maybe in exponential sense, with exponential rate, but that would be too ambitious. Usually it's not going to happen, but some kind of flocking, okay? And typically it does require, in general, some kind of connectivity at all time. Because, for example, in the open space, you can simply put two flocks far away from each other and direct them in the opposite ways, and they will never talk to each other, right? I mean, they will never even have a chance to communicate. So obviously, it's a counterexample. So the connectivity assumption, the graph connectivity assumption is necessary in this general case, and it can be quantified. This was done by Moralik, Tejic, and Tadmor. It can be either connectivity at all time or connectivity of the initial condition, but very, very strong communication. Okay, communication strong enough for the flock to remain connected for all time. So it is the strength of communication that keeps them connected. Another mechanism to keep the flock together is to introduce some confinement force. So it's kind of two-zone model, alignment and attraction without the repulsion. So specifically for the quadratic confinement, the condition on the kernel can be relaxed to something like 1 over r squared instead of 1 over r. So, so what have we tried? So I only assume that my kernel is completely local, right? What has been tried? Well, essentially 3 parts, and this is gonna sort of define 3 parts of my talk. First is microscopic level, so the agent-based, unfortunately not much has been done, okay? So we're gonna state generic alignment conjecture and on a torus, which is the cleanest settings where I can state this conjecture mathematically. And we're gonna see some recent progress in this direction. Kinetic level, we can introduce some noise which spreads particles around with certain uncertainty, and this creates a mechanism for alignment as well. but in the sense of relaxation, okay, to a max radial. So it becomes a relaxation problem for our corresponding kinetic equation, which has also seen some progress recently. And also the macroscopic level, the hydrodynamic level, we would like to understand what level of conductivity do we need to still achieve floating. Okay, so let's talk about this generic alignment conjecture. You can state these conjectures not only, torus may feel like artificial for applications, although it may not if you look in the bulk again of the flow. But you can formulate the similar statements in the open space under confinement forces or mutual interaction, potential interaction forces. So let's just look at the compact statements. Compact because I immediately rule out that counterexample that I showed you in the beginning, right? You cannot disperse to infinity, so you're in a confined environment. But still there are problems because you can, for example, let one agent go around one geodesic, right? And maybe another agent going in a perpendicular or even parallel geodesic somewhere else. And of course, they will never talk to each other, right? Now, in order to arrange things like that, these are called locked states, okay? Their velocities have to satisfy certain rational dependency property, right? So there's actually, it's a very known result in ergodic theory, Kronecker. So if you look at this ensemble variables, right, where you put all the coordinates of agents in one variable and all the velocities in another variable, and these live in this big ensemble space of Rn and T and N, what you see from here, because they don't interact, it's just a free motion, right? It's just a Euclidean line in that big torus, right? And that Euclidean line doesn't really fill the entire torus because some agents don't come together at a certain distance. So there are certain open subsets of the torus that will not be filled. So when this happens, the coordinates of this mega ensemble velocity vector have to be rationally dependent. Okay, and in fact, always this line will fill a k-dimensional subtorus where k is the rational dimension of all these coordinates. Okay, over the field of rational numbers. So, so what does it say? It says that the set of these velocities has measure 0, right? So generically, this should not be happening. Okay, generically they should come at a communication range. So here's the generic alignment condition. For almost every initial data, solutions to Cucker and Smale system will align. I am not conjecturing any rate because there may be some transient period when they travel free, then they communicate, then they travel free again. So this rate can be very, very slow, but it should in principle be true, okay? Just by intuition from this criteria. So what has been done? In 1D, it's all recent. In 1D with Helgi Dietert, we settled this in one-dimensional case. Now, in one-dimensional case, it's just too topologically restrictive, right? Because you always communicate. You don't have this problem with locked states, but you still have to do some work because there's a lack of coercivity in energy inequality, so you have to fill in this gap. So we introduced a certain method to do that. The conjecture is true for the sticky particle model. So if you have two particles, when they approach communication range, sticky particle formally corresponds to the case when the communication strength is equal to infinity. Okay, it's a characteristic on the ball, it's equal to infinity. So when they come together, they stick and they travel together, right? And the new momentum of the new cluster is the average of the momentum of the previous clusters. So the reason why the conjecture is true is because there is still a memory of the initial condition. So when new clusters form, they form rational combination of the previous coordinates, right? So if the previous coordinates are rationally independent, then the new ones are going to be rationally independent, right? So in other words, if you start from rationally independent velocity coordinates, you will always remain like that. So it will not be possible to form two or more clusters in the end that will never collide, because that will create rational dependence of the velocities of the cluster. So, so that's the conjecture for sticky particle model. And you might think that, okay, so maybe rescaling time or rescaling the kernel, you can sort of approximate smooth model. You can sort of imitate the dynamics of the smooth model by a sticky particle, but it's not the case. The smooth model, unfortunately, doesn't have a lot of memory of the initial condition. And so you cannot quite connect this rationality to the rationality of the initial condition. So problem becomes much more complicated, but it was settled for when the number in any spatial dimension, but the number of agents is 2. So two-body problem, basically. Okay? Actually, it comes as a byproduct of a more general result. If you have any number of agents, then generically at least 2 will align. Okay? So to prove this result, we sort of adopt a statistical mechanics point of view. So we look at the ensemble as a whole, and we're looking at so sort of geometrical interpretation of alignment would mean that that my system converges to the diagonal, right? So diagonal in this ensemble space is a measure 0 set. So a prerequisite for alignment would be that my Cucker-Smale semigroup should contract volumes to 0, right? So somehow, maybe in some directions it will not converge to the diagonal because of these locked states, but it should contract. So it should form this kind of squeezed regions, right, around the diagonal. Well, the question is it going to be around diagonal or not? So that is the alignment question. But can we at least prove that the volumes contract to 0? So if you look at the Liouville formula, you can actually solve for the Jacobian, and the divergence, fortunately, of the Cucker-Smale system is rather simple. It's just the sum of all communications, right? So all I have to do is to prove that this integral of the sum is going to infinity, right? Well, the thing is, if it's not, then there will be some fat blob somewhere here which does not contract, okay? And if you have this fat blob, the semigroup will almost preserve its volume. Actually, not preserve it, but it changes it by a constant factor. And so you are in a confined environment, so you're going to be coming back to this blob infinitely many times by Poincare recurrence theorem, right? When you're coming back, so what it means is that there will be a pair of agents, I and J, that will come together at the communication range. And that means that this phi, by continuity, is going to remain bounded from below by a certain constant on a certain interval of time. So overall, you will build up those masses of communication overall for infinite time. As time goes to infinity, this integral will diverge to infinity, right? So it's kind of becomes inconsistent. It's like either, it's an alternative, like either agents never interact at all, or they interact infinitely many times, right? So it is that pair of it, and if this sum, integral of the sum goes to infinity, then at least one of them, one of these, for one pair of I and J, the integral of the communication will diverge to infinity. It is that pair that will align. Okay, that requires another argument, but that's the idea. So for n equal 2, that's true. Unfortunately, for even n equal 3, we don't know. So to move to the other 2 parts of my talk, I need to put it in the proper perspective. So we study the large crowd limits, so mean field scaling. This was formally derived by Han and Talmor, 2008, and then proved by Han and Liu. So the empirical measures corresponding to discrete dynamics will converge to distributional solutions to the corresponding velocity alignment model. So it's a transport model which encodes the alignment force in a very similar way as in discrete. So here, rho density and momentum are macroscopic, and my strength function becomes dependent on the density, and my averaging operator also depends on the density. So for the Cucker-Smale model, this actually has a very nice continuous formula, continuous representation. So this is just this kind of a modification, density-weighted modification. Rho sub phi means modification with the kernel. There's actually a whole ecosystem of other models except for Cucker Smale. So if you modify your strengths and you set it equal to 1, this actually takes care of some of the anomalous scaling issues that appear in Cucker Smale if you have one small flock and one large flock. So this was proposed by Moch and Tucker in 2011, and so this creates another model. Okay, so the same averaging but the different strength function. You can actually, so this averaging by itself is not symmetric, but you can over modify it one more time, and this modification actually has many interesting properties. So that creates another model. So there's actually a whole ecosystem. It's a mathematically rigorously defined category of models that you can study. And one can, in fact, develop the whole functional analysis of these operators in the proper way. What's interesting is that there is actually a parallel with the turbulence. So this is what's called Favre filtration. Those who do turbulence in non-homogeneous settings can recognize this is Favre filtration. And this kind of filtration has been used to resolve Van-Sager conjecture in also in non-homogeneous settings, for non-homogeneous Euler and Navier-Stokes equation. In a positive, not the hard part that Phil was talking about, but the positive part. So there will be more parallels with turbulence later. To pass to the hydrodynamic limit, there are two regimes we can do that. One discovered by Kahn-Vasseur and Figali-Kahn. So it's the monokinetic limit. So you intensify local alignment force, and your distribution converges to monokinetic ansatz. This was done with the no vacuum condition, but I removed that condition recently. So this leads to pressureless Euler alignment system. Generally, you have this closure problem, of course, for the momentum equation, but at the monokinetic case, that Reynolds stress disappears, and you have pressureless system. The alignment force here has very nice commutator structure, and we've exploited that with Eitan in our works a lot. Then another regime is where you excite not only local alignment, but also you put some strong noise. And that results in Maxwellian, convergence to local Maxwellian. Local Maxwellian gives you isothermal pressure. Okay. So the difference between the behavior between these two systems is that without the pressure, you expect some kind of flexibility of limiting flux. The shape of the flux is not really forced to be anything by a pressureless system, although velocity has to be uniform. In the pressure case, everything has to be uniform. So these are two different regimes. So the regularity, let me just sketch very quickly some of the items on regularity agenda for this systems. Basically, we understand things very well in 1D and partially in multi-D. So multi-D generally is an open question. So for the pressureless in 1D, there is a very nice criterion of regularity, threshold criterion, discovered by Carrier, Choi, Tanner, and Tan. Because in 1D it's Berger's, right, plus alignment. Alignment does have some mild regularization properties. So your threshold is not just positive slope. You have some leeway. Okay, slope plus convolution with the density. So as long as that quantity is positive, you're good. So you're globally opposed. Actually, this is physical quantity. It's conserved, happens to be conservation, and it's actually related to Brezhnev-Jordan entropy. It's actually a derivative of the kinetic part of the Brezhnev-Jordan entropy. There's actually a whole hierarchy of entropys you can develop for these models. Later, with Eitan, we looked at the singular communication. Okay, so this puts it in the realm of fractional parabolic systems with drift. In 1D, it's globally unconditionally well posed. We did it using Caffarelli-Chen-Vasseur kind of regularization results. And alternatively, Doh, Kiselev, and Ten approached it with from the point of view of models of continuity. So in multi-D, there's a spectral dynamics, there are some special symmetric classes of solutions like unidirectional flow, radial flows, and then there are general results for small initial data in multi-D. Okay. For isothermal pressure in 1D, only small initial data, and with Konstantin and Rivas, we discovered this entropy hierarchy method where you can prove global opposons also in 1D, but when you also have another local diffusion, okay, like non-homogeneous Laplacian. So let's look at the, I'm gonna actually switch the order of my parts of my talk. So I wanna talk about hydrodynamic level first, okay? Partly because it sets the stage for the kinetic part. So let's look at pressureless Euler alignment. So this is the system, okay? Let's look at the energy. It's Galilean invariant, so we can assume that the total momentum is equal to 0. So if I want to prove alignment, it means that velocity has to go to 0, right? In particular, I can look at the energy dissipation. So one way to see alignment is just to show that the energy goes to 0. It is some kind of a weak sense, alignment in the weak sense, in the L2 averaging sense. But still, that's the first thing that is available to us when you look at the equation. So you have very nicely looking energy dissipation term over here. So you can see clearly that as long as the flock remains misaligned, it burns energy, right? It tries to go lower. The question is, how do you quantify that, right? So you can write this expression as the scalar product of U with LU, where L is the alignment operator. And then you look at variational problem. Just look at the infimum of these ratios. It's non-negative. And if it happens to be positive, then we are in a game. Because then I can replace this back with the energy, and I obtain this kind of Gronwall inequality, right? So as long as this spectral gap, lambda, is non-integrable, so it remains wide enough, then I will align. Again, no rate will be claimed, but it's still the energy goes to 0. So the question becomes how to compute the spectral gap. Now remember, we work with local kernel. I cannot simply just replace phi with a constant from below. If I could do that, this would be exactly equal to the energy, right? And I would be, this lambda would be just a constant. And then obviously the alignment would be exponential. That would be Cucker-Smale theorem. But phi is local. So what do? Well, one way was proposed by Nathan. You can actually look at this expression and do some kinematic estimates. So the estimates he obtained is rho minus squared divided by rho plus. So rho minus is the infimum of the density, rho plus is the maximum of the density. So this is basically done by removing rho's, working with what's left, and then putting rho back together. Once you remove rho's, you get rho minus. Once you put it back together, back into the equation to recover the energy, you get rho plus. So if we momentarily just forget about rho plus, suppose that it's under control, then the criterion for alignment becomes rho minus is greater than 1 over square root of t, something like that, right? So the density cannot go below square root of 1 over square root of t. So the big issue here, which is great, in general, this is the best we can estimate. But here is the issue with the rho plus. We rarely control this quantity, okay? And especially this will be prominent in the kinetic approach. So the idea to get rid of rho plus, the idea is to introduce a new method of estimating this spectral gap. It's called lower energy method. So let me just describe in words what this is. So if you look at the energy and the energy law, I don't want to write it like this, actually. I don't want to write it, I mean, it looks very good, but it may be sort of, you're going to be stuck with this formula if you look at this one. So I want to consider this just as a difference of inner products, okay? So without any massaging of my equation, without any symmetrization. just keep it as is. What I see here is two energies. One, well, it comes with the weight. The density is the initial weight and also the communication strength. Okay, and one is sort of numerical value of the average. Okay, I'm going to call these two energies, E1 and E0. I'm going to introduce the whole hierarchy of low-tier energies. So now I'm going to take average and average. Next, I'm going to take average and double average. Then it's going to be double average, and so on. Turns out that this is a monotone family of energies. And not only it is monotone, even the differences, which are the dissipations, okay, are also monotone by Jensen inequality you can derive. So instead of looking at the top tier difference here, which when I estimate it, it always gives me this rho plus, I'm going to look at the lower tier. Okay? This formula is a little bit misleading. We're not going to replace this diffusion with the worst diffusion. I mean, this is a bad thing to do. What I'm claiming actually is that if I can estimate the spectral gap for my lower tier energies, so if I can say that epsilon 1 minus epsilon 2 is greater than some, so this is not epsilon, this is E's, greater than epsilon E1, this implies, just by operator calculus, that my needed gap is the same. Okay? Unfortunately, this is not the energy, this is not the physical energy because it contains this strength function, so I will have to replace it with another rho minus because the communication strength is convolution, rho convolution with phi, and then I recover my real energy, okay? So the question is how to compute this epsilon. This doesn't bother me because it's rho minus, not rho plus. How do I compute epsilon? So this is what is kind of the essence, this simple implication is the essence of the lower energy method. And turns out, oops, sorry, yeah. So turns out that the formulas for these differences, I mean, now we kind of try to make them look like this, but they look more sophisticated. In fact, for some, I mean, this is the formula for the Cucker Smale, and some other models have even more bulkier formulas. But the advantage of this is that I don't see any rho pluses here anymore because, see, what happens is you pick up more densities on top, 1, 2, 3. But then the density that you pick up on the bottom is always convolved with the kernel. And that is always bounded from above, right? Because by L1 normal the density times L infinity normal the kernel. I have no problem with the rho plus anymore because it appears in convoluted version. There are some variable doubling convolution operations that are involved, but basically, if you go down to the computing actual spectral gap, for the lambda is going to be the product of these two, is going to be rho minus to the fourth. For epsilon specifically, let's remember this formula for the next stage is going to be rho minus q, okay? So the criterion becomes weaker than in Ayton condition, but so it's 1/4 root of t, but it doesn't require any rho plus. So can we improve that? Actually, yes, we can on the hydrodynamic level only. So there are a lot of biological studies in experimental biology that suggest that in the actual flight of birds, they don't really feel Euclidean distances, they feel topological distances, where communication propagates faster in thinner regions, right? If there are fewer birds in one direction, I can communicate faster in that way. So this can be encoded into communication kernel. So in our work with Ayton, we did that in a very specific way. So we introduced these communication domains, which are symmetric, mirror symmetric and axisymmetric regions with angles at the ends being less than pi for technical reasons. And so we're saying that if x communicates with y, it will have to communicate with agents in the middle. And if the mass of this region is small, then my communication has to propagate faster. So it has to be, the kernel has to be inversely proportional to this topological distance, which is the mass of this region between x and y. So we've done this because it already introduces necessarily singular kernels. So in order to develop good well-posed theory, we have to really dive into the realm of fractional Laplacian. And so this becomes so that's why we introduced another kind of geometric part to it as well. So it's partly topological, partly geometric, and the model itself looks exactly the same as the previous case, but now this becomes more interesting because the kernel actually depends on the density by transmitting this information in various regions differently. And it turns out that with this modification, we could lower the requirement of the density by quite a bit. So 1 over t. So 1 over t. If that's true, then the float will align slowly. Logarithmic, I mean, with local communication, you never expect something like exponential. But at least logarithmically, ln to the power 1/6. What's interesting is that in 1D, this is not an assumption. That automatically is true. So if your flock initially is non-vacuous, it's always going to be bounded from below by 1 over t. And the reason behind it is because we still have that magic E quantity, the entropy, preserved for topological model as well. So that makes it possible to estimate the floor of the density. The regularity theory for this model is quite complicated. I'm not going to get into details. Even local well-posedness actually is complicated. So in this paper over here with my postdoc Daniel Lear and my student Nick Reynolds, we try to recover the classical Birka-Tomaida criterion in order to apply it to recover classes of global solutions like unidirectional flows, small initial data, things like that. But for that, we needed just to control just one gradient, because if you want, if you need to control more, the math becomes quite a bit more complicated. So to go down to a criterion with just one derivative, you have to use paradifferential calculus with quartic paraproducts, which is quite technical. So simply because you have u raw unknowns, another raw here, and when you test it with another u, you have 4 products. So 4 tuple products. So so let's switch to the last part, which is the kinetic point of view. So looking at this problem of locked states, right? One way to disrupt them is to introduce a small noise. Okay, I want to look at the same discrete system as before, but now with a small noise. It's weakly multiplicative, so my multiplier here is just the strength function, which depends on the density, not the velocity. Okay, and sigma is a small parameter. So what this does is it introduces noise where the flock is, and it disrupts those unnatural rational rotations. So we expect that agents, when they disrupt it, they will start interacting, and eventually will align. So on the kinetic level, this results in corresponding Fokker-Planck alignment equation. So this Fokker-Planck alignment equation will have the corresponding strength function in front of the diffusion, right, coming from this noise, which creates a lot of problems because a priori we don't know how lower this can go, and if this can go low, then we lose that noise, right? It becomes degenerate. What do we expect though from this? We expect that as time goes to infinity, the solution will relax to the global Maxwellian with standard deviation given by sigma. And so now, if we let noise go to 0, we sort of kind of going back to the deterministic. Of course, the Maxwellian concentrates at one point at the center, which is the u bar. U bar is my average momentum. You can always assume it's 0 by Galilean invariance. So alignment in these settings can be understood as a double limit. First, you study your behavior, the behavior solution as time goes to infinity, and then as noise goes to 0. Exactly the same way we understand turbulence. That's another analogy that I would like to draw. The turbulence, you first let your solution settle on the attractor, so you first let time go to infinity, and then you study statistics on the attractor in the vanishing viscosity limit, right? That's exactly the same here, except the attractor here is just 1 point, okay? So that stage is trivial in that sense. But how do we prove that? Well, that's the question, especially with the presence of this degenerate wave. So this program has seen partial progress in the past. So Duan, Fornazier, and Toscani addressed specifically the Cucker Smale case, and they proved the relaxation result in perturbative seconds. So when you're already near the Maxwellian. Choi in 2016 did the same for the, not exactly Cucker Smale, but a problem with the local alignment. Okay? So same perturbative seconds. When you have perturbative seconds, you avoid a lot of issues having to do with the irregularity, with the roughness of the macroscopic field. And he was able to prove the same result. These techniques were inspired by collisional, the techniques that appear at that time in the collisional realm in Landau and Boltzmann equation by Gu, Duan, and others. And so that was sort of the end of this story. Now looking at Cucker Smale, so I always want to, I don't want to introduce the more general result, which will look very confusing. But just for the Cucker Smale, we were able to actually settle the global relaxation problem. So you don't have to look at the situation near Maxwellian. It's actually true in general. So you start with any initial condition. So HKL is a specially weighted solar space. And when you work with kinetic equations, the classical results, the classical solutions can be, estimates can be closed in this weighted solar spaces where weights increases with the regularity in the kinetic direction. It's kind of classical. But we need to suppose that the kernel itself is Bochner positive. So it's the convolution of another kernel with itself. That's not really a big restriction, because if you want to look at local kernels, okay, so if your C looks like this, well, your phi is going to look like this, right? Its support will just double, but it's going to be local. So you can reproduce a lot of local kernels in this particular form. But we need that in order to ensure that our Cucker Smale averaging is positive semi-definite, in order to have a chance even to look at this spectral gap computation. So if that's the case, then the density gains support from below at any positive time. I should have said from time equal 1, because we're still looking at long time here. Of course, when t goes to 0, then this bound deteriorates. But at any finite time, it builds the support from below. And that's important, because that's the only thing that we care about here. And the solution relaxes exponentially fast with these particular rates to global Maxwellian in L1. Of course, it will relax in the relative entropy sense. But what's interesting here is the rates. So the rate here is sigma to the power 1 cube, 1/2 from enhanced dissipation. You would expect maybe 1/3 rate, but we haven't done this analysis. So this is what comes from the method. So to prove this result, there are several ingredients. So first of all, we have to develop proper global Poison's theory in weighted summative spaces. Second, very important, is gain of Gaussian tails. I will make some comments about it a little later. It's a common effect, but the point here is to prove this uniformly for all time. Then we estimate the spectral gap, as I already said, as a cube of the lower bounding density. This is where we use the Bochner positivity. And Villani de Villers hypocoercivity method to put it all together. Okay? Actually, I'm going to start with the last. So you rewrite the equation in terms of this normalized distribution, F over mu. Mu is the global Maxwellian. You can write your equation in this drift diffusion form. A is the A is the gradient, A star relative to the Maxwellian weighted inner product joint, and B is the transport. And it turns out that, so without all these ingredients, this would be just the Fokker-Planck equation, and that would be a classical result. But here we have degenerate diffusion, and we also have this extra alignment force. So we're looking at the relative entropy, and it turns out that the entropy has two different forms, and these two forms play, in both of them play important roles. So the first form is you sort of look at the classical part, okay? So what this generates is what's called the Fisher information, okay? This expression here, it's sort of it's a diffusion. But unfortunately, it's degenerate because it diffuses only in V direction. Also, this is the byproduct of the alignment force, right? And this is positive definite, so it has the wrong sign. So we have to fight it. How do we fight it? Well, there is another dissipative form of the entropy, okay? So I can rearrange this term in a different way. Forget about the residual Fisher information that I get. Just look at this difference. This is exactly the same spectral gap, the same difference of energies that appeared in hydrodynamic formulation. So it's this difference here, right? So I'm going to use low energy method to estimate my epsilon by rho minus. Okay, so it enters into analysis in this entropy inequality. If I do that, then so this right-hand side will be replaced just by constant multiple of the energy. And I can combine the two forms together to kill this residual energy coming from the line. So then I keep both, right? I have my cake and I eat it, in a sense. So I have the Fisher information and the energy with the right sign. Okay, but I still lack the Fisher information in x direction, and that's where the Villanidi-Villiers comes. So what's interesting is that when you work out so what you do is you work out the equation for the mixed information, for the x information. It is the mixed one that recovers you the minus ixx, right? And then when you put them together, this better be small, so that the combination of these three information becomes equivalent to the total Fisher information, which controls the relative entropy by the log-Sobolev inequality. So what you recover by the method is, of course, this important latent term, but then there will be information in V direction and the energy coming with the wrong sign, but you can kill that with the entropy, right, with this one. And in the end of the day, you obtain Gronov inequality and exponential decay. This constant C5 encodes that sigma to the power 1/2 that I was mentioning. Somehow it comes from this method. So in order to prove, okay, I already said enough about spectral gaps. I'm going to skip that. The last piece in this proof is obtaining Gaussian